Okay, so I'm Jan. Thank you for having me here, but also thank you for bearing with the projector issues. I'm here to talk and eat pizza, so that'll be good. For those that don't know me, which I guess is most everybody, I'm from Arizona State University, with a closing parenthesis that's dangling for some reason. That must have been a copy paste error from somewhere. I'm a professor at ASU. I also am very passionate about the capture the flag community. So I've been competing in these cybersecurity competitions for basically a decade now. 2 years ago, I took over hosting of DEF CON CTF. As well. So at ASU, we do a number of things. We organize CTFs like DEF CON. We do we compete in CTFs, and we do a lot of research into program analysis and very specifically binary analysis, and more broadly, cybersecurity. Today, I'll be talking about angr, as you guys have heard, which is the base of our program analysis research. First, some background. The background we're going to start with is the Cyber Grand Challenge. angr was born actually before the Cyber Grand Challenge for a completely unrelated purpose. angr was born to A, facilitate our research into binary analysis, but B, automate playing CTFs for us, right? We were getting a little older. angr started out in very late 2013. I was in my late 20s already, and I just knew that I didn't have much time left where I could just spend an entire weekend without sleeping to capture flags. I needed to have a program that I could just run that would capture flags for me. Shortly before we founded angr and started developing this project, there was like the first Plaid CTF. Have any of you played Plaid CTF? Yeah, so Plaid CTF is a very good CTF that runs every year. First edition of Plaid CTF, I literally stayed up for 48 hours straight. Zero sleep for 48 hours, and that worked. Second edition, I couldn't do it, and so on and so on. So I knew my time was coming. We needed to do something automated, but also I needed to publish papers and finish my PhD, so we needed a base on which to do binary analysis. So we started angr, we started pushing it forward, and then in 2014, the Cyber Grand Challenge was announced. Cyber Grand Challenge was a large, fully automated capture the flag competition that was played by 7 computer opponents with 0 human interaction. These are the 7 machines here in the top row, in the front row, that on stage in Las Vegas in 2016 battled it out in kind of a cyber warfare scenario to determine the best of the first autonomous hacking systems. One of these was mine, or was made by the team that I was leading at the time, Shellfish. But why did the Cyber Grand Challenge arise, right? So I created angr to help me, or I started down the path with my colleagues of creating angr to help us do research and to solve CTF challenges for us. Why did DARPA, the entity that created the Cyber Grand Challenge, also the entity that funded the creation of the internet, why did they dump something like almost $100 million on this competition, right? On setting all of this up and so forth. For a very similar reason, it turns out. Basically, hackers are like roses. Hackers start out in a general population of computer science people, maybe not even computer science people, and there's just something special about them. At some point, you in this room realize you're a little unique. You want to drill down and understand how things work at a deeper level and break them, put them back together. in a way that maybe your fellow students don't or aren't interested in. And it's something that is extremely hard to teach, and then in fact, we haven't figured out how to teach it. I also teach courses, right? I've recently created a online platform to try to teach cybersecurity, and in all of this time that I put in at ASU and before that during my graduate studies at UCSB and as captain of Shellfish and so forth, the thing I realized is you are either a hacker at heart or you aren't. It's actually very hard to turn someone that is not a hacker into a hacker. There's something that has to come from within. And so it's very hard to find these unique roses, right? But let's say that we could create a robot that is a unique rose, that is reliably. You push the power button and you boot up a hacker. Then you have one hacker. If you have one hacker and another human hacker, you can't just duplicate them. It's very hard. It's very hard to duplicate a human being. But it's not hard to duplicate a computer. Once you have one hacker program, you can spin up duplicates, spin up more and more copies, and have more and more hacker programs. Whoops. And the idea for DARPA, and the idea for us creating angr, is to create a crowd of automation that can help us hack, right? So, how did the Cyber Grand Challenge go? The Cyber Grand Challenge was actually fought, the final event was fought between these machines on stage live in front of thousands of people. It was really crazy. It's very hard to see in this photo. Over here, there is a kind of a side area with couches and stuff where they force the teams to just watch their machines battle. They actually had a air-gapped, government-enforced like separation between the humans and the machines. There were like armed guards standing to make sure you didn't go and like plug a USB stick into your machine to try to give it directions or anything. It was pretty awesome. Our machine, of course, was right there, battling out with the rest of them. We managed to get a team together, coordinated enough to have matching t-shirts. That was a big win, considering how completely uncoordinated we were. And in fact, we were so uncoordinated, we never really, as much as students, we never really created something very reliable and very functional and continuously functional. This competition took place over 11 hours or 12 hours or something, right? So it needed to, the systems needed to keep working for a very long time under kind of adversarial conditions because they attack each other too. In a practice round, which was hands-on, this is a photo taken back at our lab. This was in Santa Barbara at the time. In a hands-on practice session, our cyber reasoning system, as these things were called, partially failed. The database crashed, right? And these practice sessions were extremely valuable. There were very few of them. You couldn't miss a practice session because you needed to understand how the game worked and how the kind of orchestration of the game was set up and so forth. So rather than call the practice session a wash, we spun up what we then called a paper database. This is actually our database for an entire practice session of the Cyber Grand Challenge, where we were writing down the results of our various components and making API calls into our system to try to like actually do something with the practice session, right? So we were fighting this under very adversarial conditions. We tried to do a code freeze. Farnsworth, in this case, was the component of our cyber reasoning system that tracked all of the information that it knew about. And then at some point you're like, all right, like good cybersecurity or good software engineers, we're going to do a code freeze. This was about a month before the competition. It's going to be great. We're just going to do bug fixes from then on. This happened like 3 days later. So we definitely didn't quite know what we were doing. There's a lot of good tales like this. At one point, we had to pass some data to some other data, and this was after the code freeze. And my colleague Antonio, teammate on the CyberGrand Challenge, said, Jan, I need this data for patching. I need to pass in the type. And I said, no, we've code frozen. We can't do it. And Antonio said, well, Jan, you either let me do this or I quit. I'm going to walk out this door if I can't put so it was very rough conditions. We were working like crazy, not just on angr, but on all of the orchestration around it, up until the moment they cut the cable. They literally cut it with a pair of scissors. The moment they cut the cable to our machine, somewhere on YouTube is a whole time lapse of this entire evening. That's me, you know, in the final run up to the CyberGrand Challenge. This is literally the day before the competition. And then we created something that actually fought this cyber war, right? That actually managed to do autonomous hacking. The final results were pretty cool. We got 3rd place. For getting into the top 7, you won a prize of $750,000, and for getting 3rd, there was a prize of $750,000. And so we ended up as the richest CTF team in history with $1.5 million. So it was very painful to you know, step down as Shellfish's captain, because it was awesome having control of that money. I point out a lot of things usually when I talk about this. One, we're the top university team, et cetera, et cetera. These red and blue bars, it was offense and defense. And we have the top red bar and tied for the top blue bar and so forth. What really sunk us was strategy. The mechanical fish was really, really, really dumb. So all of the program analysis was great, but then once you actually try to figure out how to apply it to a cyber security game scenario, we just had hard-coded rules that turned out to be very stupid. So we have an article that we wrote up, as you can find, where we go very in-depth analysis of the results. The very important thing to point out is that in the history of automated cybersecurity competitions, the mechanical fish, our cyber reasoning system, is the only one in history to ever get a palindrome score. That's our major accomplishment in the CTC. So, now that we have motivated why we need automated cybersecurity, let's talk about angr. Angr, of course, is the system that underpinned all of our program analysis in the CyberGrand Challenge. I should say most of our program analysis. So for much of our vulnerability discovery and for all of our patching, we used angr, and for the other part of, and our automated exploitation, for the other part of our vulnerability analysis, we used a fuzzer called AFL, and I'll talk about what fuzzing is in case you guys aren't familiar. Just as an intro to angr, angr is really a library, a collection of useful modules and analyses. It's not a tool, and in fact, a lot of people's difficulty with it comes from treating it as a tool. Angr is designed to be used in pieces and rearranged to fit the problem domain that you're dealing with. And it's extremely flexible. It supports insane amounts of architectures, and this list is growing. We're working on P-code support to add in things like Sega Genesis and all sorts of other crazy stuff. And it has a whole bunch of kind of dirty hacks and principled algorithmic program analyses and so forth that all together combine to do a whole set of program analysis capabilities on a whole bunch of different binary formats. And non-binary formats too. You'll notice angr can consume Java bytecode, for example, and analyze this Java and actually also Android applications. So that's angr. Now we're going to really quickly dive into program analysis background before we dive into angr's actual capabilities and so forth. So, who here is an expert in reverse engineering? How about program analysis? All right, perfect, because then you would have been bored. So this is fairly introductory stuff. We're going to try to push through it so we have more time for kind of hopefully hands-on demos. But we'll start with the basics. So when you're doing program analysis, you're not just doing program analysis for fun. I mean, some people do program analysis for fun. I'm actually one of these people. I enjoy just looking at disassembly, right? I have a colleague, my friend Fish, who actually, he would be perfectly happy if all he did in his entire life was look at the disassembly of binary code. But usually that's not an end, it's a means to an end. So the means to an end implies some goal, right? What do you want to achieve in your program analysis? And generally what you want to achieve is some understanding whether or not the program holds to a specification or violates it, or something along these lines. So if you are reverse engineering a license key checker, the specification is the license key checker will only validate license keys provided by the vendor when you actually purchase a piece of software. And of course, what reverse engineers do when they crack that is they figure out how to violate this specification. A specification might be that the program has no way for user input to hijack control flow. That's a very reasonable specification. The goal, as I said, is to verify the specification, and the technique is basically how we will verify or violate the specification. So let's rewind back to the dawn of computing. Right? In the 1930s, I just completely went blank. The guy, he made a machine.
Charles Babbage.
Yes, thank you. The Babbage made the analytical engine. And he published like a number of designs of it, and just kind of almost more philosophy and math than computer science, but it is the first design of a device that is kind of recognizable as a computer. It was a machine that could be programmed, that would carry out operations, that had input and output. It was the first computer in some sense. There was never an actual machine built. There are actually some emulators online of what Babbage's machine might have been like. But the first thing we were really interested in, the logo of Ida, the disassembler, is Ada Lovelace. She was the first program analyst in history, actually, because Ada Lovelace read Charles Babbage's designs and actually published analyses of programs running in these designs. We'll see later how Ada Lovelace actually invented, by accident, some of the techniques that we implemented in angr, right? One of these techniques, as a way of looking ahead, is symbolic execution. It's when you look at the symbols actually running through a computer. If you have, variable x and variable y, and then when you add them, you know this is x plus y. You track the symbols instead of the values, and this is actually what Ada Lovelace did. This is one of her publications where she runs through manually the execution of some programs, to calculate Bernoulli numbers or something. But she goes through cycle by operation by operation. So this is one CPU cycle, and this is her writing up what the machine is doing at that point. It's from her note G of her publications, right? So this is one of the very first pieces of program analysis from 1842. This is a very old field that we're diving into. This is Grace Hopper, moving forward over 100 years. The inventor of the first compiler, right? So the inventor of the first compiler suddenly gave program analysis a very strong reason to exist, right? Compilers had to create code that was performant, right? They had to read in whatever source code, COBOL in this case, compile it, output something that would actually run fairly fast, but also the compilers had to be correct. So we had programs whose correctness was absolutely critical to the functioning of, at first, military applications, and of course now increasingly our entire society. And we started in with the question of, can we actually analyze these programs to make sure that they're correct? And we started in with manual program analysis with Alan Turing, who is also yet another person that is known as the father of computing. And Alan Turing wrote a really interesting article in 1949 in which he describes the process of checking a large routine for bugs, like a function. And if I remember correctly, his large routine is, by modern standards, of course, laughably small. You have Google Chrome, which has megabytes and megabytes of code. This large routine fit on like a page or something. So it's the very first step, and he says, okay, the computer first looks at this. Excuse me. Throughout the paper, he keeps using the term. The computer looks at this. The computer looks at that. The computer calculates the intersection of whatever variables, et cetera, et cetera. And I'm reading this. When I first read this paper, and I'm wow, this guy is such a visionary. He already is thinking about computers checking computer programs, right? And at one point he used this strange term, I don't remember it exactly, but something like, at this point the computer has to ask itself something. Like, that's a weird thing to say about a computer, right? Computers don't usually have introspection. And then I realized that he's not talking about machines, he's talking about computers, as in human people that did computation in those times, right? So he's talking about manual program analysis, and this is where it really starts, and this spawns the field of program verification with this idea that we are going to take a specification, such as the program should not crash, and we're just going to figure out, can it be possible to violate the specification, or alternatively, the way it's usually stated, can we guarantee that this specification holds, right? So can we guarantee that this program will never crash for manual static analysis, or for manual program verification, let's say? No. You cannot guarantee that this program will crash. Why not?
Unreferenced memory, or unassigned memory, right?
So all of this is somewhat safe, right? I mean, it's fine. You write into A, B, and C, 3 numbers, and then you have a crash in the program, right? So there is a crash in the program, but it's guarded by a guard condition, where you have A plus B has to be C, and C minus B must not be A. So this is just an offhand example, with the idea being that this should never be able to be true, right? This is always false. So this program won't crash, but it's actually very hard to say that. And if you have a smart enough analyzer, you can't say it, right? So you can take this condition, you can take that condition, say these can never be true at the same time. There's a Boolean and, so this program is never going to crash. We can verify it, but it gets more and more complex. So now you have our Fermat's last theorem here, right? So if you have 3 A, B, and C, where A to the third plus B to the third equals C to the third, and they're not 0, the program will crash. Now this is hard. There's a problem that stumped mathematicians for hundreds of years. Is your program analyzer going to tell you that this can be verified? It likely won't. It won't be able to figure out what's going on there, and it won't be able to guarantee you that your program meets your specification. Right? And what will end up happening is what's called a false positive. You will end up in a situation where, because the question you're asking is, can you guarantee to me that this specification holds, the analysis has to say no, I can't guarantee to. And so now you think this might be insecure, but maybe it's really not insecure, or it might violate the specification, maybe it's not violating the specification. So people moved on to software testing, from program verification to program testing, right? And program testing has a slightly different twist. Program verification verifies that a program conforms to the specification. Program testing shows that it doesn't. It gives you a counterexample. Say, this is a violation of the specification. This is a crash. But it says, okay, if I can't find a crash, I'm not guaranteeing anything. There might still be some bugs. I just haven't found them. The easy counterexample for this program, with just squares, of course, is if A is 3, B is 4, C is 5, this program will crash. You can find that using, for example, symbolic execution, and produce a counterexample. You have now been a successful program tester in this scenario. The origin of program testing is back in the punch card era. Thank you. In the punch card era, you had to test your code because it was a giant pain in the ass to, like, you know, debug or you ship your code, it doesn't work. They have to ship you the cards back so you can figure out what's going on. It's a nightmare, right? So people would test their code fairly carefully, and one technique of testing code was what was called trash decks. So cards that were discarded, thrown into the trash because they were buggy programs or something. They would be taken from the trash, shuffled up, and fed as input into programs that people needed to test to try to trigger corner cases that these programs hadn't considered in the processing of input, right? This is now called fuzzing, 70 years later. And whereas verification tries to verify logical properties or for an absence of crashes, as we discussed, testing with these various techniques, we're still talking about manual techniques, right? These card fuzz, the trash decks were put in manually, tries to identify counterexamples of a specification. Now let's move into automated techniques. With the development of compilers, the proliferation of code out there, it quickly became impossible for people to check their software for bugs. Was that a hand?
No, sorry.
Cool. And it also became very necessary, as I mentioned, to enable efficient generation of the resulting code, right? So when you have a compiler, in order to optimize code in a way that makes it run fast, you have to perform a lot of interesting analysis that we can have a whole class on. Does UC have a compilers class? Yeah, I recommend you guys take that. It has a lot of the inverse of these concepts. But there's also kind of the more, you know, nefarious angle to this whole program analysis thing, and it's hunting for vulnerabilities, right, automatically. Vulnerabilities as a area of study were first brought up in like the 1960s. This is the first paper that I could find going way back when that talked about memory corruption, right? This is the first paper to bring up the question of, hey, what if user input that we have in our program overwrites some metadata? That would be pretty weird, right? Roughly around the same time, well, actually significantly later, people started talking about logical vulnerabilities, like backdoors, right? So Ken Thompson proposed, hey, you know what would be crazy if you backdoor the compiler so that whenever it compiled anything, it would produce things with a backdoor in it. And if you use that compiler to compile a new compiler, your new compiler would end up with code to produce backdoors into the compiled program. Pretty trippy paper, and people started really thinking about, okay, but now we need to actually verify not just the compiler, but the result of the compiler. We need to verify the binary software, because that's the only way we're going to find these maliciously inserted things in our compilation. So there's like all sorts of specifications you want to enforce, various goals, various techniques, and now let's dive into the ones that are truly automated and the ones that work on binary code, right? As I discussed, if you want to truly look for vulnerabilities that arise as a result of the compiler screwing up or being compromised, you need to use binary, or you need to look at binary code. If you want to be general and be impactful in your analysis, because binary code is everywhere, you are all holding devices that run binary code. And the binary code in your devices is like insane. It's written in memory unsafe languages. Right? Who here has used C? Out of those who use C, who has gotten a segmentation fault? Yeah. And I guarantee you, the devices that you're using have all of these same bugs that you were making. They're just better patched up, right? But they're there. The fastest growing language in 2019 was actually C. With all of our crazy new memory safe languages and all of this, we're still using C, still introducing memory corruption bugs and all of this that we have to find. All right, let's get into some prerequisites for program analysis. First is the concept of a basic block. If you have a program, there's going to be a Python example on the right, and you're going to have a mock compilation on the left. So let's say you take an input X, right? Already in Python 2, that would be a vulnerability. Then you check for the value of that, and you say either correct or not correct. One part of your program checks for input, then your program splits, and one part says correct, and one part says not correct. Right? Fairly straightforward so far. Every set of instructions, and in this case there's really only one of each, that run together before branching are called a basic block. And those are basic blocks. These basic blocks have edges that represent these control flow, essentially, right? And these edges have conditions on them. To take the left edge, X has to be 42. To take the right edge, X has to not be 42. We call these constraints later on with symbolic execution and so forth, but they are fairly straightforward, right? They're introduced by conditional branches in the program. Pretty simple. If you take a whole big program and you build a graph of the basic blocks and the edges between them, and of course each edge has some constraints, what results from that is called the control flow graph. It's the graph of the control flow of the whole program. And every execution of a program will take one path through this graph, right? From the beginning to some endpoint. And there might be multiple endpoints, because there might be multiple places where your program terminates. Who here has taken like combinatorial algorithms and graph theory and stuff? Yeah, so a lot of static analysis, a lot of program analysis that doesn't involve actually running the program is basically huge amounts of graph theory. If you dig into angr source code, there are insanely clever tricks and topographic sorts with various corner cases for various worst case performance scenarios, and it's a nightmare. But it definitely helps to know your graph theory and actually to know your discrete math, a lot of concepts of computer science. You remember the constraints that we were talking about? The constraints along a path are called path predicates. So a path through the program is equivalent to a set of constraints onto the input of the program. It doesn't just have to be user input. It could also be input from a network, input from a Google search result, input from files on the computer, all sorts of stuff. But constraints on this input have a one-to-one relationship with paths through a program. Does that make sense? If you have a simple program, check your input does something, you give it the same input, it'll have the same output. How do you deal in this scenario with randomness? Randomness is a source of input, the random seed, right? Same input, or really the same constraints on an input are associated with one path. And you'll notice multiple different actual inputs can take this path. X is 41 will take this path, as will X being 40, and so forth. Well, actually this path, no. Only X 1 through 7 will take this path. But there's a one-to-one between constraints and paths, but a one-to-many between constraints and actual instances of inputs that match those constraints. So this is kind of a view of program execution in the abstract. This was used to create one of the first automated analysis systems in the 70s. Right? So you'll remember we started talking about memory corruption, et cetera, in the late 60s or something. We started talking, Alan Turing was talking about checking routines manually in the late 40s. In the 70s now we have arrived at symbolic execution. And symbolic execution, here's a slightly more complex program in Python again, but we'll pretend that it's something like binary code for now. Symbolic execution basically says, okay, remember those constraints? Let's just gather them all up. So we have an input and a check against the username. This is a case where there's a program. If you give it a command code of 7 and a username of service, it'll crash. I mean, it's a toy program. It's impossible to write a very interesting program that also is easy to demonstrate. So this program is kind of dumb, but it does the job. So it'll crash if it has a command code 7, and then otherwise, if you have a username that is not the hard-coded username of service, it will actually perform an authentication. It's a hard-coded credential in a way that you actually do see in like real firmware that is actually deployed in the real world, right, in embedded devices. In fact, this username service, who's heard of the Mirai botnet? Yes, the Mirai botnet, huge bot infestation from 2016, 2017, something like that. It spread by using hard-coded credentials in routers. And one of its hard-coded credentials was username service, password service, right? So, and then there's a hard-coded backdoor. So this is, like, as stupid as this is, it actually happens in practice. So in symbolic execution, we start executing and we say, okay, if, well, let's first continue laying out the program. So here's, one side of that control flow. Here's the other side, and then going on with this side, right? If the username is service, it checks the command code. If the command code is 7, it'll crash. Otherwise, it won't crash. Then it exits. So that's already 2 paths down this program. On the other side of that first conditional, we take a passcode, and then we also check it and so forth and exit. All right, you'll notice that for this authentication call, we're just kind of combining it into one graph. Obviously, an authentication routine would also have its own control flow graph and so forth, or we combine it into one block for kind of visibility's sake. So, how do we do symbolic execution? Recall our constraints. We basically step through a program and we record all the constraints and all the potential paths that can be associated with this program. So we're stepping forward, we hit the first if statement, we got our username that's checked, and so we say, okay, Username check, there's an unknown username, but if we go here, we have a constraint that that username has to be equal to service. If we go here, we have a constraint that it has to not equal to service. And then we keep going, and then we hit this major problem, right? Because there's a function called to A2I. Who knows what A2I does? ASCII to integer. A2I is implemented by looping. Right? You have to loop over the input, figure out with a string input of, alphanumeric or numeric string input, what is the number that it represents. So you might have 10 as a string, and then you return 10 as an integer. This is a fairly naive A2I implementation, but all A2I implementations are roughly they are equivalent to this, and they exhibit the same problems. Symbolic execution. So imagine that you are symbolically executing this code. The very first thing that happens, you have that big chain of if-else statements. So the first thing that happens is your symbolic executor is going to spin off a new state for each one of those. If you recall, every time that we have a check, we branch into two and kind of explore both sides. So already for the very first letter, you already have 10 potential, actually 11, 0 through 9, and a non-numeric input. For each of those, for the second letter, they're going to have 10 as well. And you have an extreme, what we call state explosion, in something as simple as A2I. That's very bad news. We don't really have a good answer for this, which is embarrassing, as we're like a society that sends Teslas to Mars, and we can't deal with state explosion. The best we typically do is just kind of force reduce states, which is equivalent to just saying, you know what, toss out most of these randomly, most of these randomly, most of these randomly, keep it kind of to some reasonable amount. And the problem is that we might not be able to capture all constraints properly, and we have to ignore certain scenarios, and we might never be able to trigger this crash because we can't execute through A2I properly, right? So that's symbolic execution. We might leave a number of things unexplored. I mentioned Ada Lovelace earlier. This column right here is the first instance in history of the symbolic execution of a program. It's very, very crazy, from the 1800s. What she did basically, there were variables that were being assigned results, etc. And she said, okay, well, here is, the variable, the value of whatever variable here is 2 to the 2n, and then there was some, -1 of whatever, and this is the statement right now, and etc. And she just tracked it through, which is actually very similar to what angr does. So now we've added symbolic execution as a potential technique. What about something that can deal with this path explosion? The path explosion, our biggest problem from it is a problem of coverage, right? We start being unable to reason about certain parts of the program using symbolic execution because we just undergo this huge rise of complexity that we don't have techniques to manage. Are there other ideas where we could analyze a program without having this exploding complexity? It turns out yes. A husband and wife team in 1977, just 2 years after symbolic execution was invented what is called a static analysis. It's an analysis that doesn't involve running the program. Symbolic execution, in some sense, we ran the program. We didn't run it on a CPU that reasons about ones and zeros. I mean, we did in the end. The analysis runs on the CPU, but the program doesn't reason about ones and zeros. It reasons about variables, right? Static analysis doesn't even run the program, not in a traditional sense. It just looks at it, and it tries to reason about these variables abstractly. Cousseau invented abstract interpretation. And with abstract interpretation and static analyses in general, we're not going to dive very deeply. How long are these meetings?
Until you're done.
Okay. I literally taught a semester on this, so that's a. That's true. All right, so we'll just let me know when we're kind of sorry, because we'll then go hands-on, and that'll take some time. Anyways, I'm gonna save the actual details of static analysis to then, but basically because they're not as they're not as approachable as symbolic execution. But static analysis takes a look at the whole program and tries to identify possible alerts. Static analysis is a technique that's very well geared for program verification because it will look at everything. Whereas symbolic execution is a technique that's more geared for program testing. Angr does both. Your static analysis, which should be there on the top right, I must have screwed that up. We'll do a bunch of analysis on the full program, and it'll give you alerts. So it says, okay, on line 5 there's a possible crash, and that's great. That there is a crash. We'll also give you a bunch of false positives. Let's say there's a possible crash on line 13, even if there is not. What happens? The reason that this occurs is that to achieve the scalability needed to run and analyze the full program that symbolic execution lacks, static analysis has to make trade-offs. Imagine that you're looking at a program as a human, and the program is huge, and you can't look at it all without turning your. Anyone ever use like a 48-inch monitor as a monitor, and you can't actually see it all? You have to turn your head. That's symbolic execution, but you can't turn your head. Your head is stuck. So one way to deal with that is to move back. But suddenly you can't see the screen very well. So you start, it's too fuzzy. So you start over approximating. Say, I can't really see that very well, so there might be something fucked up there. That's the static analysis. So now we have static analysis, specifically Cousseau created abstract interpretation. It is the abstraction of multiple program states that symbolic execution suffers into these sort of abstract states with abstract variables that lose precision and lead to false positive identification of crashes. And then we mentioned fuzzing. So manual fuzzing appeared in the 50s or late 40s. Automated fuzzing appeared in the 80s. It was the last of these techniques to be automated. And it basically just sends random crap at a program and hopes that it crashes, right? In this case, it'll try to send, username ASDF password 111. It'll trigger some part of the code. It'll start randomizing things in there and tracking how that changes execution. It suffers, the base technique suffers from this inability to target things. It'll never randomly generate the word service, right? It will eventually, but it's going to take a very long time to randomly come up with that string. So all of these techniques have flaws, and this is kind of my thesis for you, is if you want to find bugs, right? You'll notice in all of my examples, they were very contrived, but fuzzing fails to find this crash bug. So, static analysis finds it, but also finds a bunch of other crap. And symbolic execution fails to find it. If you want to find these bugs, or more generally, if you want to do if you want to do program analysis effectively, we're not at a state where we can take the human out of the equation yet. And don't forget that you are a human in the equation. The number one mistake I see people making with angr, like I said, is using it as a tool. They sit down, they import angr into IPython, and say, solve this challenge for me. And of course it doesn't work, because these techniques are really shitty at the end of the day. They're still, 50 years on, they're still extremely infantile in their capabilities. So, with that, let's dive into angr. All right, so what is angr? Angr is essentially a binary program emulator, with the exception of Java, but even then it just treats Java as a binary thing as well, that is able to execute programs on different domains. And what this means is it takes your hello world or your toy programs that we were talking about here, and it is able to execute it with ones and zeros representing everything, right? But it's also able to execute it with variables staying variables, symbolic expression. It can abstract variables into higher level abstracted data representations to enable abstract analysis, etc. And it all does it in one framework, in kind of the different configurations of different parts of angr. Of course, the number one design goal was making it easy to use, and easy to use interactively, and easy to use in Python. In Santa Barbara, where I did my PhD, we almost exclusively did projects in Python. This is carried into ASU as well. Who's kind of a new age hacker that use like Rust or something? Anyone use Rust here? You'd have a bad time. Do you like Python?
I like Python.
All right, good. So you're a reasonable person. That's good. I have some students that, I have a student that showed up and said, you know what? I'm gonna write my own program analysis engine in Rust. And he's using angr now. So, the basic idea behind angr, behind any program analysis thing, is you're gonna take a basic block, you're gonna execute it, emulate it on a data domain that is very rarely ones and zeros, and then you're going to see what the block does. And you'll build the facts of many, many different blocks together. There's a lot of caveats to this, but this is the basic core capability that any program analysis tool needs. And these blocks, they impact program states. Program states consist of register values and register in symbolic mode or whatever, expressions and so forth. Memory, files, the state of libc, various states in the kernel, network connections, etc., etc. You have to track all of this stuff to analyze real-world software, right? And all of this stuff is extremely hard to track. And all of this stuff can be either concrete values, ones, zeros, etc., or these sort of symbolic expressions that you can reason about later, etc., to enable different types of analysis. Angr should now be not a giant headache to install. When we first open sourced it, it was quite a doozy, but now there's a Docker container, auto-updated anytime you push to master, and you can just Docker run angr/angr, and it drops you into a shell where you can run IPython and do stuff. That being said, if you want to use the graphical user interface that we'll talk about today, you'll probably have to install it locally. If you install it, please use a virtual environment. We don't test anything with virtual environments, and there have been cases of uninstalled scripts blowing away global things. Just don't let us fuck up your system. Use a virtual environment. Angr has a whole bunch of stuff. You're gonna have kind of a, like I said, I taught an entire semester on program analysis with angr. But we're gonna have a very high-level view of 3 different main modules that angr has, which is angr itself, the actual program analysis component. CLAY, which is a recursive acronym for CLAY loads everything. It is our binary loader. And clarify, which is a very Pythonic, clever pun on the word clarify, because it clarifies understanding. Anyways, which is what we use to deal with different data domains, is the domain engine of angr. We're going to use a guinea pig that exists in the angr test cases. It's a simple example, the very first program that we managed to run in angr. Sometime in 2014. And it basically implements something like a backdoor. So if we just run it, now we can make that bigger. Actually, let's make sure. Yep, okay. So we run this, ask for a username and a password, and actually because this is the first one that ran with angr, it needs exactly 8 letters for the username and the password, and it just tells us to fuck off. Right? It has a backdoor in it, but we don't know what that is, right? But we'll figure out with angr. So that's the first binary to ever run in angr. Man, we had a party when we managed to run this thing. So let's get started. First, we're going to load this binary. So I'm right now already in my angr virtual environment. Like I said, don't install it globally. It is not ready. I mean, it is ready, but we don't want to deal with that. All right. So we import angr. This is I'm doing some development on the parts of it, so there might be weird print statements. I didn't get a chance to stash everything properly. But we basically load the binary into an angr project. Yep. Okay. And it takes some suspiciously long time, but I'll tell you why later, and it returns. Now we've loaded the binary, right? The caveat, the reason it took a while is by default it also loads all the libraries. In this case, we don't want that because it makes all the analyses take longer, so we'll go back and disable it in a sec. But first, let's look at all of the things that we already right away have access to programmatically. One of them is CLAY. It is the result, or the loader object, which is our loaded program as loaded by CLAY. CLAY can load everything, but really it can load ELFs, which are the binary format used by Linux and the BSDs, or most of the BSDs. It can load Mach-O files from Mac OS. It can load class files for Java, and can load PE files for Windows. And it can load just binary blobs. But right now, we loaded fullware, which is an ELF, a Linux binary. In here, we have a bunch of different objects. We have the fullware binary, we have libc, we have the Linux loader, we have some internal mappings for hooks for angr specific stuff, and like thread local storage, and etc. Right? But these are the three main things. These are the three binaries that were loaded when we created that project. That's why it's a project, not a binary. Because what we did was load three binaries into the same memory space: the actual application and its libraries. We can look deeper in here. So we can look at the main object. Of course, that's our fullware binary. And we can look at its imports, its sections, all sorts of different things. So the fullware binary imports puts from libc, printf, read libc start main. I mean, this is similar to what you'd see in any sort of reversing tool, right? And you can look at symbols, where they're defined. There's a bunch of symbols in here. Destructors, I don't know why the blank symbols are showing up. That's weird. We have, where's my mouse? There's my mouse. Stir comp, I mean, all sorts of stuff, right? You can get actually a lot of other information, right? I mean, if you don't know the architecture, you can get the architecture. You can get the, is the entry point here? You can get the entry point in this object. Fun fact, if we go to all objects and we look at libc, nope. Wait, yeah, sorry. I can't array today. Did you know that libc has an entry point? You can actually run libc. So can we do a path here? Oh, file name. Okay, hold on. Does it save the file name? Now we've reached the me crawling through IPython part of the tutorial. Oh my god, there's so many things. I didn't see it. Oh, yes. There. All right, so we can actually run libc, and it like runs, and it tells us version info. This is I found this out by accident one time. Yeah. Did you know that you can run? So if you look at, you know, the libraries loaded for a very simple program, you have libc. You can run that, and you have the loader. Did you know that you can execute the loader as well? You can execute the loader and have it load things and run things, and which is what roughly happens when you run a binary period, but it's fun fact. Okay, so you have all of these objects, you have the main object, you have a lot of information about them. Already this is pretty useful, right? So there are projects that use just Clay, open source projects around that you know need a binary loader. They use Clay. Clay is completely decoupled from angr. In fact, we enforce a very strict one-way flow of dependency. Right? There's no inner dependencies in the angr suite. The idea is that these side effects of creating a program analysis engine should be also usable by the community. For a while, ClarifPy was being used as the data domain for another program analysis engine, actually. I don't know if it still is, but it was for a while. So that is Clay. You can continue to crawl through it, of course. Anything else I want to point out? Yeah, you can look at. Oh yeah, you can look at the sections. Who here's familiar with like sections versus segments in a binary? It's a fun thing that was explored for a while in CTF problems circa 2011 or so. The basic idea is segments define how a binary is loaded. Sections are just there for debugging and reverse engineering. So sections are never actually consulted when the binary is loaded, even though they ostensibly say a superset of that information that segments do. Using contradictions between them, you can make program analysis tools do crazy things. Anyways, that's Clay. Let's move on. Let's jump into angr and see what kind of analyses you can do. So the very typical static analysis that we do is called the control flow graph recovery. You all know now what control flow graph is. And we can just go cfg project.analyses.cfg. This will take forever as it's, well, that scrolled off. It was warning me just now that, hey, you loaded the libraries. We're about to do CFG recovery of libc. This is going to take like 10 minutes. So let's not have it take 10 minutes. There is a option to the project creation, which is basically says don't load the libraries. Auto load libs equals false. Another fun fact of angr development is that this specific option has gone back and forth as to the default, like probably 4 or 5 times. We're constantly having arguments. Should we load libraries by default or should we not load libraries by default? We haven't really figured out a good default yet. So now we don't have the libraries. Now we can do this much faster. Boom. That was how fast it took to calculate a CFG because this program is extremely simple. What can we do with the CFG? Well, we can see how many blocks there are. All right, so we can do nodes in the graph. Apparently, that is deprecated now. angr is also an active research tool, so it's constantly changing. Basically, every time I give a demo, and it's also very large, so I can't like be on top of every single change and so forth. Every time I give a demo, something breaks. So in this case, don't use this. This is deprecated. There's probably a better top level thing also. Maybe get all nodes. That's a terrifying name. What is this model thing? CFG model. All right, we'll just do what it says. Okay, so here's all of the nodes, all of the blocks in our control flow graph. And you can see they're, whatever, different blocks at different addresses, of course. And there's a graph. It is an actual graph. It's backed by a network X graph. Network X is a Python graphing library on which you can, run all sorts of analyses. So I can actually say, let's say I have this node. Can I just get a node? Oh my god. Network X is upgraded since the last time. Get any node. Let's get this node. Yes. Beautiful. And let's get another node at random. And then maybe there won't be a path between them or whatever. So, oops. Here's node 1, here's node 2, and then can we do cfg.graph dot, and then there's all sorts of stuff. There you can run all sorts of graph stuff. Excuse me. There should be a pass. No, come on. Okay. Hold on. We can. Network X is a little import, unwieldy sometimes. Network X dot path graph. No. Shortest. Yes, shortest path dot. Yes, there's a function. Perfect. So now we can give it our CFG graph. We can give it our node 1 and we can give it our node 2, and it says no path between them, right? But just by looking at this, we see that there's an authenticate function. So for example, we could grab that node, grab the node for main, figure out a path between them, and start reverse engineering this binary in IPython, which is a terrible idea, but it is possible. You can also say things like, okay, in our node 1, how many successors does it have, right? How many potential future nodes can it get to? And you say successors, and this is, yes, successors, and we give it node 1. It says that node goes straight to the fitting function. Or we could say what calls that node. Nothing. So it must be in some finalizer array or something. So this is how you use the control flow graph. While you're creating the control flow graph, it also recovers data dependencies. So you can also query those. Who here has used like IDA-Pro or Binary Ninja? So all of the information that you have in IDA-Pro, Binary Ninja is accessible programmatically here. As a human, you probably don't want to actually access it in IPython unless you're doing an automated analysis, right? As angr learns more and more about a program, it fills out a knowledge base. So a knowledge base that I'll point out is what is called a call graph. So these are all of the detected functions in the program, and then, or the addresses of them, and then these are all of the edges between the functions, right? So functions that call each other. We can actually grab the function that's at the very end, start of the project, of the program. So you recall there's an entry point that angr gets, so there's the start function. You can look at all of the blocks in the start function. There's only one. There's a block that sets everything up and calls libc start main. And various other things. You can, for every function, you can see, okay, what are the code constants in here? So angr actually uses this to identify, or we use it sometimes in angr to identify common crypto functions that use specific constants. So you can say, here's this function. Let's look at constants that you see in the code. Boom, there's like a bunch of them, and so forth, right? But this is getting a little tedious to look at manually. We're going to look at manually, or look at in IPython. We're going to look at one more thing, and then I'll show you the GUI. I mentioned we can get blocks. There's only one. For this block, we can, of course, print it. And this is the start of the binary, sets a bunch of stuff up. One of these is libc start main. This is not AMD64. Did I load the wrong one? I loaded the wrong one. It doesn't matter. All right. This is x86. So we set everything up, call libc start main. But like I said, angr does analysis on all sorts of different architectures. So what we tend to use is what's called an intermediate representation. The one we use right now is called the vex. It's an intermediate representation that angr actually first translates this to this. You can see that's a kind of a lot more, but it's easier to programmatically parse. So if when you look at, you know, and ESP blah 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 blah, right? What is that instruction doing? It does a bitwise and, right? So it's clearing out the last nibble of the stack pointer, aligning the stack pointer to 16 bytes. But that's not all it's doing. Also updates conditional flags in the processor. That's also not, it also changes the instruction pointer. Every instruction changes the instruction pointer in some way, right, to the next instruction, except for this guy that changes the instruction pointer radically, right? And all of this you just kind of have to know for every architecture. By using an intermediate representation, we get every single effect recovered automatically for us. But this looks like it's optimized, which we probably don't want. But we're not going to do well on that. So the point is, angr internally uses a representation called vex. It's the same intermediate intermediate representation used by Valgrind. Who's used Valgrind? It's like hunt down memory leaks. Yeah. So we basically took all of their hard work and stole it, but it's all open source, of course. And we use their intermediate representation to reason about individual blocks. And as I said, that is the core thing of program analysis engine. So building out around that, of course, is not trivial, but making this is extremely tedious. libvex is like 1 million lines of code, or I don't know, several 100,000 lines of code of lifting different architectures into Vex. This might look ugly, but it's actually not that bad, right? This is just telling you where the instructions are. So this is one instruction. This is the next instruction. Put will write to a register, so this writes this value to EBP, nice and simple. This retrieves a 32-bit integer, signed integer, otherwise it'd be U32. It gets a 32-bit integer from, oh no, sorry, the sign, never mind, ignore that. This gets a 32-bit integer. This does a little endian load of memory from this temporary variable, which is the stack. So this does a stack load. This increments the stack. This is a pop. So, oh no, it doesn't. Never mind. Yeah, it doesn't do that. Anyways, the point is, this deconstructs an instruction that can be fairly complex into individual little statements with no side effects. Is that a hint?
Yeah. Why is the put EIP not in every one of the IMARs?
This is optimized by default. Let's get a non-optimized one, and I'll show you what that looks like. Hold on. Now we have to remember, is it op level? Op level. These things keep changing. Okay, so here's the same block with no optimization. Now you have each one has to put EIP and all of this. Right. So now with this, we can actually go through like step by step and be at a consistent state at the end of every instruction. When we optimize, we do cross-instruction optimization, or libvex does cross-instruction optimization. We add to that a little bit so that we have to process less code, but then that means if you stop analyzing in the middle of a basic block, you might not be in a state that makes sense. That's a mild trade-off, but it's good for performance. But now this is the true representation of exactly what those operations do. And so here, let's see what happens. Yeah, so this was a pop. So you get the value of the stack pointer, you load little endian into T3, then you add the value of the stack pointer, you add 4 to it, later you store that into the stack pointer, you store T3 into ESI, and you put the next instruction address into your instruction pointer. This was pop ESI. If we scroll up, yeah, it's right there. All of this, right now, it's pretty printed for human consumption. It's not very pretty, but it's printed. Internally, it's stored in very nice to process data structures, and it's a good way to write a program analysis engine. That being said, we're also looking at other intermediate representations right now. The NSA recently released Ghidra, which has a representation called P-code, which is also very cool. So we might use both in the future. And if you want to write something that, you know, tries to understand all of the basic blocks in the program or something, it's very simple, right? You go through, iterate through every node in a control flow graph, and for each one, you try to translate it. Done. This actually is kind of our first example of angr in for CTF purposes, right? My favorite type of challenge is shell coding. At DEF CON 2 years ago, I had a mega polyglot challenge where you had to write shell code to run on like 11 architectures unmodified, same shell code. I think the top team managed to get, the top team that did it the intended way managed to get like 7 or something. So a shell code that runs the same exact binary bit stream runs on 7 architectures. It's pretty awesome. The way I approach shell coding challenges is like this. I enumerate the input space. So who here has done a shell coding challenge in CTF? Awesome. What's the last shell coding challenge you've done?
It's just a simple system sh kind of call.
Yeah, but what were there like restrictions on the shellcode?
No.
All right, so there are shellcoding challenges that have restrictions on the shellcode. The shellcode that you can provide. HitCon in 2016, I think, had, or maybe it wasn't. I think it was HitCon. Had something called Holy Shellcode, where the shellcode had to be in Unicode Hebrew, right? So there was like very, very ultra restricted shellcode. How did we solve it? This exact thing. Basically, I enumerated all possible bytes that we could use. It was very easy. It's just Unicode Hebrew. There's like, I don't know, Hebrew doesn't have that many letters. And from there, I lifted all of them to Vex, and I was able to query programmatically in angr, give me all instructions that I could possibly use to write to RSP. You know, give me everything that I could possibly use to move data between RDX and RAX, stuff like that. Just by querying this, these blocks are actually very queryable. So here's our Vex guy. Boom. Basic block. Statements. There are all the statements. So now we can say, okay, give me all the statements. I think it's this. How is this? S for SN. No, it's not that. Let's do S dot tag. Okay, IST. Okay, let's just say that's right. So here are all the put statements. These are all the statements that write to a register. And here are the this is the register value, the offset into the register file. We're getting kind of deep here. I didn't expect to get this deep. So angr models registers as another memory space inside your CPU. So there are offsets. 24 is like the offset of RSP or ESP or something. I don't remember, but it's easy to look it up. We have Arch Info. It's a little module of information about architectures, or there's also project.arch, which is the architecture. And then we have that registers. And then we say, what's register 24? Our register names. ESP, yeah. So for every basic block, you can figure out what modifications it can make to what registers. So we do this. So here is all of the things this block modifies all together. We can put a set on that. So these are conditional flags, and these are registers. And then, so that's what it modifies. And then we can also get from the expressions so statements are things that modify the state, like write to a register. Expressions are things that query the state, like reading from register. And these are all the things it reads. So you can now start creating, for a shellcoding challenge, synthesizing these basic blocks by hand, lifting them, this is very easy. So you can actually create project.factory.block. I'm gonna have to query this. And you say byte string, p, let's say. And it needs an address at where it is for like it, because various internal reasons. Oh, Python 3, come on. There. And this is my block. This, what does this do? This just pushes RSP a bunch, I think. ESP. Push EX, sorry. See? So you enumerate the bytes that you can input safely in your shellcode, lift it all up, and then figure out, let's do this. We'll grab the vex from this, and then here are the statements, and here are the expressions. So this queries EAX and ESP, and it modifies the AP and ESP. Right? Pretty cool stuff. And then, of course, you can add more and more conditions, et cetera, et cetera. And this is my standard approach to shellcoding challenges. In HitCon 2017, there was a challenge where your shellcode had to be the name of an organic chemical, right? Like an actual like organic chemical. Our organic chemical ended up being like kilobytes in size, and we used this to synthesize possible shellcode snippets and put them together. It's a very powerful technique, and this is just this, right? Basically with some if statements added. Who followed all of this list comprehension and stuff? All right, good, awesome. All right, so let's pull out angr management real quick. Angr management is the graphical user interface of Angr. This is a bit harder to install, but we package it in a portable manner. So if you go to GitHub angr management, that's our screenshot. You go to releases. We're getting nightly releases working right now. In the meantime, we have something that we released a month ago. You can grab this alpha 2. This is an ELF. This is an EEX. We don't have a DMG yet, but we will. You download them. Oh, we do. Oh, amazing. Yeah, that guy's for Mac. Download it. Let me just show you. Download. Oh, that's gonna take a while. Really? Nope, it's fast. Okay. It'll sit here for 42 seconds. $30 seconds. 30 seconds again. 29. Feel like I'm down now with the final countdown. 10, 9, 8, 9. Who you guys been to that time? Nice. It's an exciting event. Woohoo! Okay. Let's boom, and this is it. We just execute it. And holy shit, it actually worked. So, it's that easy to get started with Angr. This is IPython. Everything that we just did, you could do from in here. Right? So you can say Angr, and boom, it's already imported for you, of course, from some monstrosity temp directory, but that's fine. Angr, there's already a project loaded. I forgot. Oh no, there's not because I didn't load it yet. So let's. Where do I get to? Yep, there we go. Let's load bin false. Okay, nice and simple. Here's bin false. Or actually, let's load code angr binaries. Yeah, let's load our binary. Okay, without the libraries, but we can also load the libraries if we want to. So here's our library in angr management. Right, so now we should have project defined. Yep, error execution aborted. That's interesting. Well, something got fucked up. Anyways, it was also 2 months old, so it could be completely broken. This is our function, our main function. You can see it calls puts to write out the username for us, blah, blah, blah. This is ugly to read, right? Luckily, angr has a decompiler. And the decompiler is getting better and better every day. So this is the decompilation of this function in angr. Right now, something that we're working on is my mind just went blank. What are we working on? The type recovery, right? So we can automatically create structures. And then whenever like reverse engineered complex object-oriented code in IDO or Vidra or anything, it's a giant pain. Although internally we're already automatically doing a lot of that. So we're exposing that to the interface right now, but it's fully usable reversing framework. You can click around, kinda. Hold on, let me open up a non-old version of this. Now we have, while it loads, it gives you a whole like splash screen. That took a couple months to implement. All right, binaries tests. All right, let's look at the state of decompile. Boom, see, already a little better. Still some ugliness there that can be eliminated, but we can see that we ask for a username, read that, ask for a password, read that, and then call authenticate, and based on that, either reject or accept. Let's see if woohoo! Here's our project, and from in here we can do all of this this stuff. We can actually change how the decompilation works. We can turn off the simplification of stack canaries. Oh, there were no stack canaries in here, but in general you can modify how decompilation works and so forth, and use this as a reversing tool. And it will increasingly become more and more useful. You can also perform symbolic execution right from angr management. So we can say, no. You can hit new state, and gives you a state name, Docker style. Say where you start the state from. That is that the start. Let's look. No. Okay. Did this assembly go to start? What's going on? As you can see, we haven't necessarily learned to make better code since the SideGrant challenge. All right. Anyways, uneven fox. We create this state. All sorts of options we can modify, etc. We're just going to do a symbolic execution. We hit OK. Where's our state? So something got fucked. All right, something broke. So let's move on to symbolic execution outside of angr management. There's a new interaction point for that. that we're gonna use. We were previously using project factory block and etc. Let me get rid of this guy, go away. Okay. So let's get our project back. Okay. We create a symbolic simulation manager. Oops. And it's go project.factory.simulation manager. All right. Nice and simple. It has one active state. We can look at this state. This is an angr state representing registers, memory, etc. Example, this is RAX at program start, 1C. Our SI, if you recall, it got popped at the very beginning. Oh, this is before the very beginning. So RSI starts out at reg RSI 0. And of course, you can grab the address or in a less magical way. Here's RIP. Oops. God damn it. That active. Yeah. Boom. If you just want to play with one state, there's a shorthand one active. It gives you just one state, and then you can tap complete through all of that. Very cool stuff. Then we can just start stepping, right? So we step, and now we're somewhere else. If you go regs RIP, we're somewhere else. We executed start and ended up elsewhere. For example, now RSI should be popped, right? Yep, now it's 1. We can see what are the actions that, let's step one more time actually. So you've stepped a couple times now, right? That last step was a little longer, probably something happened. We can look at the history of the block, of the state. These are the basic blocks that it's executed. This is an internal, this is an address where angr loads libc. If you're interested, where is it right now? You can use project.loader.describe address. So right now it's in libc init info where. Wait, that's not, is that where it is? Oh yeah, okay, that is where it is. You can see what actions it has taken, and this is very useful. Oh, sorry. This is super useful. Sorry guys, I'm getting tired not to make typos. It's terrible. These are all of the different things that that the last basic block did, right? So libc start main, it did a memory write, a register write, and you can actually dig in and see memory write where or memory read where. So here's our action. This was a memory read. We can see what address it read from. Oops. Read from what looks like a stack address. You can see what value it read. If actual value, none. What? All right. We went off script, and as expected, things failed. You can see what registers this read was dependent on. So if you're interested in anything that was read from address that used to be stored in RAX, which you might be interested in various situations or in any register, you can actually extract that. Again, these are the offsets. 48 is RAX actually. So you can grab this action and look into it, and at some point, the register that was or the value that was dereferenced came from RAX, and so forth. And you can run until some condition is met. So you can say, let's just keep executing until, who's used lambdas in Python? Awesome. So until this condition is true, that the length of the number of active states, if you recall symbolic execution splits, is greater than 1. Suddenly we split. So who can speculate in fullware why we have 2 paths? Why there's 2 states?
So when it checks your username, it splits.
Exactly. So it's either authenticated or it's not. And you can, of course, with each of these, look at the address and et cetera, et cetera. An interesting one to understand why it split is the guard conditions. So these are the branch conditions on each one that have to be true, the path predicates essentially, or some large set of them. So if you go active 0, .history.guards, what? Can't be rename it, shit, conditions. Hold on. Jump guards. Okay. All right. So some strcomp return value had to be 0 for this guy. Sorry, this is that again. And then for the other end, has to be non-zero. Now we're getting into the symbolic stuff. Things are getting pretty symbolic in here. There's a better way by looking at on the clarify level to get into this. So you do solver.constraints. These are all of the constraints that have to be true for this path. These are the true path predicates. That previous one was only introduced by conditional jumps. There are various other ways that conditions can be introduced. These are all of them. This is for the other one. But again, the only ones that differ here is that not equals turn into the equals. Now things are pretty interesting. Now we have a symbolic set of constraints that differs between the 2 different paths, and that makes one take one path of the program and the other take the other. Let's just let it finish running. Now it finished running. There are 3 total paths. So that's weird, right? In any non-trivial program, there are basically infinite amounts of paths. They're like anything that loops over user input, for example, is a nightmare. This is a very simple one that just checks your username and password and says yes or no. Why are there 3 paths? So let's look at for example, the oops, there are no more active. They're all dead-ended. They all finished. This is a part of the state that deals with the basically operating system state of that path. And here we can dump out the different file descriptors. So this dumps out the contents of standard in, right? So the thing says username, password, and says welcome to the admin console. The first path. The second path says go away, and the third path says welcome to the admin console. There are two paths that result in authentication. So that's interesting. In the same way that we dump user output, we can also dump input, right? So let's dump it for this one first, the go away one. This all nulls. Of course, this is not a proper authentication. What about the last path? Also all nulls. There's a technical reason why this happens. Basically, part of the input to the program is the file that it reads the password out of, the correct password. That file is also symbolic. And so if you look in the constraints of this guy, you see a bunch of references to file. This is the password file that it read, right? And so in this specific case, for this guy that said welcome, it read the file, and the file, the imaginary symbolic file, was equal to this. Right? There's a constraint that says that file is equal to this. We can also, so we looked at this guy, file descriptor 3, file descriptor 2 standard error, file descriptor 3 should have been that file, but maybe it got closed. Fuck. So now we're gonna go diving off plan again. This is our POSIX plugin. Nope. Don't panic. We might fail. Alright, I think we, oh yes, dump file by path. Nope. We probably failed. Okay. There's a way to get that file. I don't remember it off the top of my head. But let's look at the last one that we didn't look at. The one that also says, the index 0 that also says welcome to the admin console, trusted user. This one has constraints, like all the others, that'll get to this path. And those constraints will define what happens to standard input. Standard input is the same expression for each of these paths, is the expression standard input, right? The constraints apply, well, different constraints. The code applies different constraints to this input. So that when it's processed through what is called an SMT solver, that basically takes all of these formulas that are added and finds most of the time a solution that satisfies the formulas. Through the SMT solver, we can get the input that will match these constraints and cause the program to print that. That input seems to be null for the username and so sneaky for the password. Maybe that is a backdoor. We can go a little further. We can grab std out, std in, and we can basically say, okay, where did it go? Does the input have to be all nulls? Because that's a pain in the ass to type. So we go std in, and of course we have to tab. Where's it? Yes. Let's read out. What? Yes, content. Okay, good. So this is the content of stdin. This is stuff I just accidentally created. So it looks like stdin, there was a 64-bit value read from stdin, then an 8-bit value, then a 64-bit value, then an 8-bit value again. And like I said, these are the variables. They don't change between the different paths. In fact, if you look at this path, it's that. Of course, the ones I accidentally added are additions, but these are the same, right? You can see they don't change. They're the same. It's the constraints that have a side effect of changing them into different values. So if you grab the username, okay, and we grab the password, this is what the imaginary, the symbolic user entered into the symbolic file. Here's our username. Here's our password, both 64 bits. We're reading 8 bytes, if you remember. And then we can say, okay, let's grab this one. In the solver, eval up to 10 solutions for the username. So these are various solutions. Actually, of course, this is a string, so let's cast to str. Cast to bytes. Stupid Python 3. These are different inputs that can go in. Let's try that for the password. Only one valid solution for the password, because this path is a hard-coded credential. Let's get angr management back up and run it on this file. I thought I would hate that splash screen, but I actually kind of like it. All right. So again, here's main. That's the decompilation. I only see 2 paths through this function. If we go into authenticate though, still some growing pains. If we go into authenticate, here's decompilation of that. There's something weird, right? There's a third weird path. Let's look at the disassembly. What happens? It loads so sneaky into, or loads the location into RDX, puts RDX into RSI. That's the second variable to strcomp. It compares something against so sneaky, obviously our password as we saw. And if it is so sneaky, if strcomp returns 0, it moves 1 into EAX and jumps to the return site. That's a hard-coded credential. It looks stupid, but like I said, this is an actual real vulnerability that happens shockingly frequently, especially in these stupid embedded devices. And it's not put in there most of the time maliciously even. It's like people see it as a competitive advantage. We can patch our customers' devices remotely because we have a credential that only we know. And why do only we know? Because we compile into the binary. No one could possibly pull it out of the binary, right? But of course, that's silly. So now we saw that. Let's go back to IPython. So now we understand the password can only have one solution because it is defined to that value by the path taken through this binary during execution and the constraints added on the input by taking that path, right? Is that strcomp1 that gets added, and then we saw it. We saw that equals 0 equals 1 of the circump red. So that's the username and password. We can also say, okay, we want a printable username. This is ridiculous, right? We can add new constraints. So here's the first. This is the username chopped up into 8 bytes, right? So you can say for each of these bytes, we want them to be printable. So here's this, and this is very easy. How do we make something printable? We say let's make it greater than uppercase A and less than or equal to lowercase z. Sounds legit? Oops, I'm not in C. This is actually bitwise and for various reasons. What's going on?
Ordinal Z?
Yeah, this I understand, but it shouldn't. Hold on. Okay. Why did that test them for truthiness? So here's the bool. Now we can also. Can we do this? No. Can we do this? That's good. Okay. So this did not work for some reason. Woohoo! Okay. So these are constraints that we just manually created that say every byte should be printable, right? And we can add that to our state. So let's actually grab the state from the simulation manager. Right, this is our okay, and we just say state solver or state.add constraints, and we put in these extra constraints, and this would add these constraints to the constraints of the state. And we have to extend that list. All right. And now, if we eval a bunch of usernames, they're printable. So let's grab the first one. Okay. What was our password? Boom. Backdoor. Another way of doing this, instead of doing this eval up to, you do state.postx.dumps 0. This was stuff I accidentally added when I read more out of standard in. But this is the relevant stuff. We can, of course, open something in writable mode and write this out. That's why, oh, oops. Okay, here it is. And now we can run it through forward. Boom. So that's symbolic execution in angr. With this, we've gone through the basics of kind of the two halves of angr. The static analysis half, we're covering a CFG, doing some of this, lifting to vex, looking at blocks, etc., and the symbolic execution, the more dynamic analysis, actually running code and emulation half. There's a lot more. We are something like only halfway through even these intro slides, but I can't type anymore. Moving on, we all looked at. We looked at the solver. We can hook code in angr. So when you get to certain binary code, you start running Python code that you hooked in. This is super useful when you're trying to do what we just did on Foware on a real CTF challenge and you're experiencing difficulties, which you always will. Every CTF organizer will run their reversing challenges against angr to make sure angr doesn't work on them out of the box. What they can't do most of the time is understand how to run angr properly, right? How to use angr properly, not just run angr. When we play CTF, for binary reversing challenges, the majority of them we use angr in some fashion. Very rarely just solve start to finish. In a CTF last weekend, I was playing with my students, and there was a, who played Hack TM last weekend? Did anyone play? There was a reversing challenge that did control flow obfuscation through signals, right? So it did control flow transfer through signals, and then it unpacked like a deobfuscated, some obfuscated code, and then it would execute that to check input. This, on the face of it, defeats angr very easily. Angr doesn't handle signals at all, so game over there. But to actually make it work in angr, I'm not going to run it because the solution runs for hours, but actually Fish, my colleague, created a much better solution and beat me to the flag, but that's fine. What is it? There's called plop. Yeah. Now where's my plop solution? There. This is how I solved it. It was this easy to defeat all of the complex control flow transfer using sec faults. I looked at the binary. It's hard nowadays to get away solving reversing challenges without looking at binaries. I'm not like a mega super reverser. The top reverser on Shellfish was Fish. He's actually still with Shellfish. He's still the top reverser on Shellfish. His office is 2 doors down from mine, so he solves the reversing challenges when we play with our students. But and he beat me to the punch on this one, like I said, because he actually looked deeper into the binary. I looked into the binary enough to understand why angr is not working with it. Then I wrote a script. This would have solved it eventually. It just would take hours to run. He looked deeper, understood why it was taking ages to run, and actually automated just the part that needed to be automated. But what I did, I looked at the sec fault addresses, the addresses of the functions that, of the instructions that were just there to sec fault and transfer control flow. And I, where are my sec fault? Oh, and I hooked them all. How did I hook them all? Oh, okay, I remember what I did. I patched the binary to have those addresses instead jump to this address, and then I hooked this address. Right, so I modified the binary to disable obfuscation, and then basically used angr to solve it. This is how you hook binary code in angr. So anytime that something would try to execute this instruction, oh no, I redirected to here. Anytime they tried to execute this instruction, or there's just some finisher function that didn't do anything, normally I'd replace, I'd hook that code and actually replace it with a Python function that would run, that would set the return address or the instruction pointer to the sec fault handler. So all I did was hackily implement sec faults in Python. There was some fix-up stuff that needed to happen. Sec faults are more complicated than just transferring control flow to the handler. They modified the stack a little bit. This is all that I had to do to fix that up. But again, I had to crawl through it in GEB to understand how the stack was getting messed up. And with this, this was enough to actually start executing that obfuscated code and waiting for it to finish. Like I said, fish stole the flag from me, but what can you do? The takeaway is you need to think through how to solve things with automation, with program analysis. Like I said before, these techniques are in their infancy. It's very easy to break them. It's trivially easy to break them. But you're not just the automation. You're an expert human getting better and better every day using automation that's getting better and better, let's say, every month. You can't forget the human side when you're solving this. One way to do that, jumping all the way to the end. Can you imagine? Yeah, okay. All right. How do you get better on this? One way is angr CTF. An undergrad at UCSB. So, an undergrad somewhere, Jake Springer, wrote angr CTF, but then graduated, and angr CTF. Angr has now changed enough in the last year and a half that angr CTF no longer runs. An undergrad at UCSB recently resurrected it. This is a CTF with like 15 levels, 17 levels in increasingly complex usage scenarios of angr. It's a very good thing to dive into if you want to understand angr a little better. It has advanced path merging techniques that it explores, dealing with shared libraries, all sorts of stuff. I highly recommend this to get started, and then what do you do from there? I mean, of course, you can start using angr in CTFs. Just try it, right? Also, don't forget to still use your brain. Angr is definitely not a replacement for that. It is an augmentation. And finally, try using angr in your research. I don't know if there's like undergrad research or what the research scenario is at UC, but you know, see if someone here does program analysis research, cybersecurity research, and do a research project with program analysis. We also actually do research apprenticeships at ASU. If you're interested in coming to ASU for like 6-month research experience, let me know. We have a how-to or a fact right here about the program. Basically, what we do is we hire you for a temporary research position. You get paid roughly the same as a grad student, a PhD student. It's not a lot, but this is academia, not Google. We just put you to work. We're slave drivers. Just do program analysis, automated program analysis day in and day out. But it's very fun. If you have any questions on any of this, feel free to email me or ping me on Twitter, or I guess I'm on your Slack now. You can ping me there too. If you grab angr and start using it, get on the angr Slack too. This is the link to get onto the Slack. Any questions you got, toss them out there. It's a fairly large community now. There's like 3,000 people or something on this. I don't remember, maybe 1,000 people on the Slack. And they know how to use angr to a good degree. The people that use it successfully in CTFs are on that Slack. Oftentimes they ask questions during a CTF, and then we're like, oh yeah, we're working on that challenge too. I play much fewer CTFs nowadays because I can't play in DEF CON qualifiers. Can't really play with Shellfish, so I actually just play with my students at ASU, but that's how it is. Cool. Anyways, any questions you got?
Where does Zardus come from?
I'll say I made that up when I was 13. Yeah, there's several different origin stories, but they're all roughly what you would expect from a 13-year-old. So then they're just stupid. We'll leave it at that. But then I already had like the email and the domain names and whatever, so I had to stick with it. That's how I think all hackers should do. You should have to come up with a handle when you're like the most embarrassing name like H possible, and for the next forever you're like known as. I mean, at least Zardus isn't horribly embarrassing, but like I don't know, known as Code Monster or something. Code Monster 007. That'd be cool. That'd be a cool handle. Maybe I should have gone with that. Cool. Thank you for having me, guys.